All right. We were talking about something. I think it's chapter 19, I think. Man, we were talking about really coordination compounds. Remember, a coordination compound basically consists of two things. There is a complex ion and there's a counter ion. And you could really have either of these things. They really are sort of like an ionic compound that sort of balance each other out. So you can have a positive complex ion and you can have a negative counter ion, and vice versa. You could have a negative complex ion and a positive counter ion in this case. And we talked about ligands that are attached, and that's the part of the complex ion part. The ligands are attached to those metal ions, and ligands are Lewis bases, which means that they like to donate a pair of electrons. And we could calculate what is known as the coordination number by how many atoms are directly attached to the metal. Remember that some ligands are unidentate, which means they bond in one place per molecule. Some are bidentate, which means they bond in two places per molecules. And there's some that are polydentate, which means they do bind in multiple places. So if you had something like chloride, which is monodentate, you get kind of a 1-for-1 for the coordination number. But if you had something like endoethyl diamine, that EN1, that's a 2 for. So for every one of those, you will get two mole atoms binding to the metal. We talked about naming these guys, and remember the naming involves the complex ion part and the counter ion part. We always do the positive guy first, then the negative, like a kind of traditional ionic compound in terms of naming. Positive guy, if your complex ion is the positive guy, then you use the regular name of the metal. We do use Roman numerals as well in these type of naming. If your complex ion is negative, then you kind of go the old school name of naming it where you had ATE at the end of it. So ferrate for iron or something like that. Also, still use like some Roman numerals as well. And our counter ions are pretty much just named by their name. So if they're a positive one, they probably will be in most cases a metal. So you could just use the metal name. If they are a negative counter ion, they could be just like a chloride or something like that, which you would just name normally. Or if it's a polyatomic ion, you just use the name of it. Remember, it doesn't really matter how many of those sort of counter ions you have, you just sort of name it by its name, its appropriate name when you do that. Any questions on any of that there? All right, then that's the ones we finished on, I think. So the next thing we're going to talk about are isomers of complex ions. And isomers are a few different types, but essentially they have the same formula, but they do have different properties. Sometimes the isomers will be connected differently in sort of space, and that does give them some different properties. We're going to go through each of these here a little bit. There are structural isomers, and structural isomers are, again, things that have the same formula but do have different bonds. And there's two types of there in terms of this. There are coordination isomers and linkage isomers, which we'll talk about in just a second. There also are what are sometimes referred to as stereoisomers. These have the same bonds, but different sort of three-dimensional arrangement of how they are attached. Could be kind of coming out or going in. And those are cis or trans isomers are optical isomers as well, which can sort of move plane polarized light. So let's start with coordination isomers. So here are two coordination isomers. Again, if you look at both of these formulas, they basically have the exact same things in it. We got a chromium here, a chromium. We got five NH3s, five NH3s. We got a sulfate, a bromine, a bromine. So they have exactly the same stuff in it, basically, on each of these. The difference is, as we talked about last time here, this here is our complex ion. And in this sort of complex ion, we have our chromium. It's attached to our NH3s. Not drawn perfectly correct, but we'll just kind of throw them up there. And also the sulfate here is attached as well. And that's all part of the complex ion, which will have an overall kind of plus charge. And we have our bromide here as our counter ion. So in the first one here, the sulfate is actually a ligand, and then the bromine or bromide there is actually a counter ion that is present. And that's different than when we look at the second one here, which is this is part of, again, our complex ion. Here we have our chromium in the middle, again, attached to our 5 NH3s. And here, though, it is the bromine that's part of the complex ion. That gives it like a +2 charge. And here, our sulfate is our counter ion. And again, obviously here, the bromine is a ligand attached in the complex ion part. So these are coordination isomers. They basically, again, have the same formula. But as you can see here, in one case, one thing is the counter ion and the other one is attached to the complex ion. And then they kind of switch it around there. And the bromine gets attached to the complex ion and the sulfate is our counter ion. Any questions on that there? All right. Now, linkage isomers are, again, the same deal, have the same formula, but the difference here is actually within a ligand. And a ligand itself may have the ability to attach in using different atoms. So, for example, when we look at NO2 minus, it can attach through the nitrogen. It could also attach through an oxygen. So the ligand itself actually has a couple of options as to what atom it may use to sort of bind to the metal that's part of the complex ion. So here we got our metal. And in this first case, it is the nitrogen that is acting sort of as the Lewis base there and donating its electrons. Here, we're using the exact same ligand on the second one. And once again, here's the cobalt attaching to the oxygen part of that same ligand. So once again, both the same ligand, but it's the attachment point of the ligand to the metal in the complex ion that's different. And that is what makes it a linkage isomer. Once again, if you looked at the formulas here, they would pretty much be identical. They'll have exactly the same formula. It's just how that particular ligand is attaching, one case here through the nitrogen and one case here through the oxygen. Questions on that there. Now, stereoisomers can be geometric isomers, which are cis or trans. And as you learn, if you take organic, essentially cis and trans means a couple of things. Cis means basically the same side. Trans means opposite sides. And in traditional sort of organic, we oftentimes talk about it in terms of the double bonded carbon. And if you have two things that are attached on the same side, that would be cis. If you have two things that are attached on opposite sides of the double bond, that would be trans. And it's kind of the same side here. Here we have a couple groups that are attached sort of on the same side of the plane of the molecule, and some are on opposite sides of the plane of the molecule. And that's what we kind of look at as well. Also in organic, you find that with alkanes. Things can be attached sort of cis or trans based on that. They're common in square planar complexes. Square planar, as you might remember, is the expanded octet, right? It's got basically a square within the plane and a couple of non-bonding electrons kind of coming through on each of those sides. So here's an example. A here is cis, and again, you can kind of look at these two groups. You could even look at the chlorines if you like, and they're on the same side of sort of the square, if you will. And this would give us our cis sort of arrangement. Here we could see our chlorines, and again, you could also look at the ammonias as well. They're on opposite sides of each other within the square, and that is what is known as trans. and it does give it some different properties depending on sort of the arrangement there. You can see just slightly different in terms of color, more yellow color. This is a little bit more pale yellow color due to sort of the arrangement of those atoms. So usually in coordination chemistry, we're talking about cis or trans in location of sort of same side of the plane or opposite sides of the plane. Here is also two more, and this is an octahedral arrangement. And here we can see our trans, where our chlorine groups are sort of above and below the middle plane of the molecule there, so on opposite sides of each other, and that gives us our trans. Here they are basically kind of within the same plane there, kind of on the same side here of the square, and that would give us our cis. And you can see here, in terms of the formula, they're basically identical. Everybody's the same. We do sometimes, and you do sometimes see those guys sort of incorporated into the name as well. So you might see cis or trans indicate sort of relationship of some of these groups. Optical isomers, these are isomers that have opposite effect on plane polarized light, and they are typically sort of chiral molecules. Chiral molecules are molecules that have non-superimposable mirror images. And that's basically like your hand. If you put your hand up to the mirror, you get your other hand that stares at it. And if you take the other hand out of the mirror, you could rotate it around as much as you like. It will never fit perfectly on the original sort of hand, if you will. Something will always be wrong. Thumbs on the wrong side, palms up and down, even though thumbs are on the right side. So they'll never be sort of exactly right. These isomers are sometimes referred to as being enantiomers. And again, plain polarized light, it goes through a polarizing filter, and we do have sort of vibrations here. You could also measure the angle of rotation, which we're not going to really get into in here as well. So there's your hand thing. And again, if you take the mirror image out, you can rotate as much as you want. It'll never fit perfectly on top of each other, exactly the same. So here are mirror images. The image one is identical to two. They cannot be superimposed. There's no way to turn them around. And it may be kind of hard to sort of visualize these, especially with these a lot of times. So models are sometimes really good. But what's happening here is as this is our original guy here, and as it reflects in this mirror, what ends up happening is actually this bond right here, as it does its reflection, this bond where these two nitrogens are attached to each other are kind of right in front. And as this gets reflected to the back, so this guy would go reflected back here, that bond now becomes between these two guys. And that is the slight difference, is this bond right here. So as you rotate it, there will always be something that is not going to be correct in terms of its sort of angle and will not fit perfectly. So that's the slight difference. You can see everything else looks pretty much identical here. Um, and nothing else will sort of fit perfectly on that rotation. So these guys are chiral and non-superimposable. Here we have a trans, and you can see on the trans here, when you do the reflection, you pretty much maintain the exact same bonds that you have here, and obviously the same ones that you got going on over here, which means if you pull that mirror image out, it should be able to superimpose on each other. That is sometimes referred to as an achiral molecule, and that is something where if you have a mirror image and you pull it out, it can superimpose perfectly on the original sort of thing. Here's our cis, and again, you see with our cis, we get that little sort of problem in terms of our connection. Instead of being connected through these two, now that connection goes to the back, and that's going to create a different sort of angle as you try to rotate things, and they're not going to fit perfectly on top of each other. Let's say a lot of times cis is a problematic thing of that, and you get that sort of thing that happens rather than the trans. Now, enantiomers, as I talked about, are two molecules with mirror images of each other that are non-superimposable. And sometimes, one versus the other can have different types of benefits. So as it says, there's some drugs are chiral, but only one of the isomers are actually effective. And because of those different sort of connections, the other one is not so effective. All right. The next thing we're going to talk about is sort of bonding that occurs with complex ions and sort of where the electrons are. And this is what is sometimes referred to as a localized electron model, the formation of hybrid orbitals, the two share electrons. Those are like our sp, right, or sp2 or sp3, sp3d, sp3d2, right? So the combination of s and p orbitals. The Vesper model does not work great for complex ions. The interaction is really more viewed as sort of a Lewis acid base, so a ligand donated electrons accepted. The hybrid model of orbitals is used on the metal, depends on the number of ligands that are there. So here are six. So that is essentially, right, your sp3d2. That is your expanded octet, right? So we got six ligands coming in. And that's going to give us really that sort of octahedral arrangement, which is that expanded octet. Now we could get, in terms of hybridization, a couple of different things. We could get sp3 hybridization, which can be more of our tetrahedral arrangement. We could also have sp3d, which is our square planar, and we could also have linear, which is sp. And they do sort of correspond a lot of times to our coordination number as to how many ligands are attached. So 2 is going to be linear. 4 could usually either be tetrahedral or square planar in terms of 4. And 6 can be our octahedral geometry. And again, this would be more like a octet rule. And this is again more like the expanded octet. Now, what happens in terms of our d electrons? And that's typically what we're dealing with when we're talking about complex ions, as the metal is a transition metal typically. And that is where the d orbitals basically begin. And there are 5 different d orbitals that are there and can have basically ligands. Now, when you have no ligands that are present, all those d orbitals are equal in terms of energy. So, in terms of energy and the absence of ligands, they are all equal to each other. But what happens when the presence of ligands start to occur is you actually get some splitting of these 5d orbitals in terms of the electrons and how they're going to be placed in there. And this splitting is what is referred to as crystal field splitting. It is the energy difference between those 5d orbitals as they split when the ligands are present. Now, that is going to affect how electrons go in. As you remember, hopefully, is if you have, say, a subshell of orbitals, electrons do go in one at a time, and then come back and sort of start to pair up. Now, we always feel electrons sort of lowest energy to highest, and that splitting can affect how the electrons basically will be there. So, for example, if we are going to fill electrons into these orbitals based on this splitting, the electrons would definitely go into the lower energy ones first. And at this point, if you have more than 3 electrons, you have sort of a decision to make, which is that difference in energy too big or not as big of a difference that it will affect where the next electron will go? So if you decide, and based on the ligands present, that the splitting is not that big of an energy difference, they will continue to sort of feel like normal and then come back and kind of pair up. Now, if you get to this part and the ligand that is present does create a very big sort of splitting that's occurring here, what will happen is when they get to the end here, they're going to decide, no, thank you, that's way too high. I'd rather just fill up down here first, and then, if necessary, then kind of go to the top. So the splitting of these d orbitals affects how the electrons are populated within these d orbitals, and that creates different types of complex ions. That creates the ions that will definitely have a lot more unpaired electrons versus ones that will have more paired electrons. So ones will be more paramagnetic versus diamagnetic, and that creates what is sometimes referred to as a high spin or low spin sort of situation. Now, energy to promote electrons are very easily as they're close to each other. We can actually calculate the splitting difference here by using a formula that you probably have seen previously, and that is E is equal to H times the frequency, H being our Planck's constant, 6.63 times 10 to the minus 34 joules seconds. That is our frequency, right? Which is usually in reciprocal seconds, are a hertz. Right. And that is based off of also this one here. C is equal to wavelength times the frequency. That is the speed of light, 3 times 10 to the 8 meters per second. Our wavelength in meters. And obviously our frequency here in reciprocal seconds or hertz. And those two tie into each other as E is equal to hc over the wavelength, because if you solve for the frequency, it is c divided by the wavelength, so you can substitute that in. So these are two equations. It really allows you to calculate the energy if you know either the frequency or the wavelength that is there. And you could calculate the actual crystal field splitting, which again is sometimes just abbreviated with a little delta for that difference in energy between them, is sometimes the crystal field splitting sort of symbol. So if we take a look at this one here, let's just kind of go through the calculation here. And if we have the absorption maximum for a complex ion occurs at 470, what color of the complex ion, and what is the crystal field splitting? So one of the things we talked about as we've done experiments, right, is you always want to choose the maximum wavelength, right, and of absorbance. And that is because when you do so, when you run your samples, you have all this in terms of absorbance. If you chose a wavelength way down here, your samples can only absorb about that much, and you would obviously have a lot of samples that would be off of the scale. That's what you do, right? When you run your thing through the thing, and he has to move the little square, right, and record the wavelength, kind of pick the maximum wavelength of absorption. One of the things that hopefully you also know is that the color that we actually see in the solution, so if our solution is red, the color of light that's being absorbed is complementary to that. So we would not set our wavelength to red. We would send it to a complementary color. So in this particular case, it occurs the absorption at 470, which is in the blue. That means that we would actually see the complementary color to blue, which is our solution will appear orange to us. Just like when you did the iron experiment way back when, you set your wavelength in this area complementary to red's color. So because we do have the wavelength, obviously we can't put it into our HC over the wavelength. These are both constants. We do need to convert our wavelength into meters, so everything cancels out. So meters cancel, seconds cancel. And this gives us really joules per atom. And since we want kilojoules per mole, we can then use Avogadro's number here and convert it into kilojoules per mole. So since we got joules per atom, we can multiply by Avogadro's number per mole. Atoms will cancel, leaves us joules per mole in this case, which obviously we can then convert to kilojoules per mole. That should be a similar calculation to one hopefully you've done previously as well. Any questions on that? All right, then let's talk about this sort of splitting. How do we know whether or not we will get sort of a big split between these d orbitals or a sort of smaller split? And it has to do really with the ligands that are present. And this is the spectrochemical series. And on the left-hand side, we have weak field ligands. On the right-hand side, we have large field ligands. So the idea here is if we had this crystal field splitting, which was large, and let's just say we had 5 electrons that we wanted to distribute, The 5 electrons in this case, because the splitting is large, would go in like so, 1, 2, 3, and go, that's too big. We'll just come down here, 4 and 5. That will leave us one unpaired electron, for example. Now, if we have the same thing here, x squared, y squared, oops, z squared. If we have the same 5 and this was a small splitting, what's going to happen is 1, 2, 3, 4, and 5, because it's not going to be that big of a difference. We would actually end up with 5 unpaired electrons. That is a very common sort of question you're sometimes asked, which is how many unpaired electrons would you expect to have in this complex? This creates what is referred to as a high spin complex. A high spin complex has a lot of unpaired electrons. They're paramagnetic. On over here, we have one unpaired electron, which is sometimes referred to as a low spin complex because it has a lot more paired off electrons than unpaired, right? When they pair off, when they're spinning in opposite directions, they sort of, for the most part, cancel each other out. So you have a lot less spin. So this is sort of how you can determine, whether or not you're going to have big split or not. In the middle, it sometimes depends on the question. They'll sometimes ask you to do it for, say, the low spin or high spin situation. And in some cases, if they don't give you that information, it may not make a difference. So, for example, if I had the exact same scenario here, but I only had 3 electrons, I'm never getting to the top ones no matter what I do, right? So it won't make a big difference as to how you distribute them. They're going to go into the bottom 3 no matter what. So sometimes it doesn't really make a difference in terms of the ligands that are present because you only have so many electrons to distribute. Any questions on that there? So let's take a look at an example here. Let's say we had our nickel Br6 2 minus. So the first thing we would want to look at here is a couple of things. We would want to know the coordination number here. And the coordination number here is going to be 6, which is our octahedral arrangement. And by the way, what we've been looking at here is for a coordination number of 6, and these are for octahedral geometry. So this type of splitting that we see here is specifically for that coordination number 6 and that octahedral splitting. So the next thing we want to figure out is what is the charge on our nickel here. So this is -1. There's 6 of them, -6, and needs to equal -2. So our nickel here is rolling with a +4 charge. Normal nickel is 28. So nickel with no charge is 28, which means if we write our electron configuration for it, it is argon 4s2 3d8. Now, nickel with a +4 charge means it has only 24 electrons. Remember, as we talked about earlier on in this chapter, when transition metals lose electrons, they always lose the S's first. So they're going to lose those guys first, which is 2 electrons. They then will lose 2 more electrons out of the D, and that means that we will end up with an argon 3d6. So in terms of this nickel, it's got 6 d electrons that need to be distributed into our diagram here. So first off, any questions on that there? So because this is a coordination number of 6 and octahedral, we're going to get the exact same splitting that we saw, which is our 2 up on top, our squared guys, and our 3 that are on the bottom. And the other important thing is the ligand that is present. So we want to look at the ligand and come over here, and we definitely see our bromine on the weak side. And that means we're going to get a small splitting of those orbitals. And because of that, we're going to actually go 1, 2, 3, and this again for the nickel. And at this point, because the splitting is small, they're not going to be such a problem. It's going to come up and fill up like normal and then come back and pair off. And in this case, we will end up with four unpaired electrons in this case. And this would also be considered a high spin complex. Questions on that there? All right. So why don't you do these two? Why don't you draw the crystal field splitting, decide how many unpaired electrons it has. Obviously individually. Nickel is 28, iron is 26. Okay, let's take a look. So we'll start with the nickel here. The En here is 0 and it's +4. So nickel here is going to be +4. So that is going to be the same one that we just did on the previous slide here. So our nickel with a +4 will have 24 electrons. And that's going to give us our argon 3d6 in this case. So again, it's going to have the 6 electrons to distribute. This is, again, a coordination number of 6, which means it's going to go through the octahedral splitting. Remember, En is bidentate, which means you get a 2-for-1 deal on that. So the coordination number there is 6, not 3. And that tells us octahedral. So again, we're going to get our splitting that's going to occur here with kind of our squared guys up on top and our non-squared guys there on the bottom. And what we have to determine is our En. So if we take a peek there at our little spectro series, it is leaning towards more the larger splitting. So we'll go with the large splitting on this. And this is going to be large or big. That means for our 6 electrons, we're going to go 1, 2, 3, and decide too big to go to the top. I thought I was hearing myself. That's sad. All right, we're going to go and pair that back off. I can just be quiet, just play the recording. Just because all right, and we'll go that way. And we're going to pair off our 6 here. So in this case, we're going to get 0 unpaired electrons in this case. And this is definitely going to be a low spin complex as they're all paired spin over here in this particular case. Any questions on that there? Coming over here to our iron guy, Cn is -1. There are 6 of them, so it's -6. We got a -3 left over. That's going to be a +3 there for our iron. Iron again being 26 with no charge. Gonna get us an argon 4s2 3d6. Iron here with a +3 charge, gonna knock off 3 electrons there. Again, gonna take out those 2, and we're again only gonna take out one of those, which will leave us an argon 3d5. So those are the 5 electrons or 5d electrons there that we have to distribute. Once again, looking at this, Cn minus is monodentate, which means our coordination number is 6, which again falls to that octahedral splitting that we've been looking at. So again, we'll get the 2 up on top and the 3 on the bottom there. And I got our XY or YZ, XZ. And again, we want to look at the ligand, which is Cn minus, and in this particular case here, we do see it on the larger size, and that's going to give us a large splitting. So again, for these 5, we're going to go 1, 2, 3. Not going to go to the top. 4 and 5 going to pair down there, ending up with 1 unpaired electron. Again, also considered a low spin complex there. Any questions on how to do this? Yeah. That's exactly right. Yeah. So typically if you have a large splitting of those, because of that, they're gonna tend to pair up more than have it go individually. And that is gonna ultimately lead you to more of a low spin complex rather than when you have a small splitting, you're gonna get everybody kind of going in one at a time, which should lead you to more unpaired electrons and a more higher spin complex. Yeah. Other questions? And that too, also, like I mentioned before, when they kind of sometimes they'll say that on problems like do it for high spin or low spin, that kind of gives you an idea of what the splitting is. And if you have high spin, you should have a lot more unpaired electrons rather than low spin, where they should be more paired up as well. All right. All right. So as you can see here, here's the one for our high spin with our F6. And again, got a lot more unpaired. And here we have low spin where we're going to pair more up because again of a larger difference and obviously a smaller difference here. That was our other example, I think, that we skipped over. In case you want to see it, that is it right there. And as was the question as well, you can see here a lot of our low spin going to result from that large difference. So we got a lot more pairing up happening over here rather than on the left where we have high spin, not as big separation. You get a lot more individual sort of electrons going in on the left. Now let's talk about some other geometries. So this is a coordination number of 4, and this is with the tetrahedral geometry. And the splitting here is basically the same, except it's opposite. So here we get the kind of squared guys on the bottom, the kind of the individual guys up on top. And it does work the same way here. If you were going to distribute, you would go 1, 2. If it wasn't so big, you would go up. And obviously, if it was big, you would go down first before you go up. And it kind of works the same way. So if you have a coordination number of 4 and it is a tetrahedral geometry, it's basically the opposite of octahedral. So again, works the exact same way. You'd figure out how many electrons you got going on there and obviously distribute them based on the ligand that is present. Now you can see this is also a coordination number of 4, and this though is the square planar. And it gets a little crazy in here in terms of all the different splittings, but again, you get some obviously lower ones and higher ones happening, and they would be filled sort of accordingly. So for us, you will not be responsible for this one because it's kind of crazy, so we won't worry about it. But you will be responsible for this one, tetrahedral splitting, which is basically just the opposite of the octahedral splitting. So you'll need to know obviously the octahedral and basically the opposite of it, which is for square planar. I'm sorry, tetrahedral. Basically the opposite splitting that happens there. Any questions on that there? All right, that wraps up this chapter 19. This is the very last chapter here, nuclear chemistry. We're going to talk about this. Good news is a lot of this stuff you've seen already because it involves kinetics, which we talked about obviously in a whole chapter. So that's pretty good. So let's talk a little about nuclear chemistry and radioactivity. When we talk about radioactivity, if something is radioactive, it will spontaneously decompose into a smaller nuclei. It is said to be unstable. Decomposing involves the nuclei emitting certain particles and our energy, which are radioactive. The one sort of going through the decay process, sometimes referred to as the parent nuclei, and that is the nucleus that's again undergoing that radioactive decay. What is sort of produced as a result of that is sometimes referred to as the daughter nuclei. If you look on the periodic table 84 and above, pretty much all those guys are going to be radioactive. And that's where a lot of the bottom 2 rows are. A lot of those radioactive guys on the very, very bottom row there as well, where uranium is as well. Now, there's different types of radioactivity, and as you might remember from your friend Rutherford, he did the gold foil experiment. He shot like alpha particles, right? Alpha particles are abbreviated with the alpha symbol. They are abbreviated with the helium symbol as well. They have a +2 and a mass of 4, and it is the helium. So they will use both of these. By the way, the top number is the Mass number, yeah. Bottom number is the atomic number. Beta rays have basically a -1 charge. They're basically like electrons. Also, the beta symbols used in a -1, or they will use an electron sort of symbol as well. So they kind of use both of these. Gamma rays, as you might remember from the electromagnetic spectrum, at the very end of the spectrum, super small wavelength, very high in energy. It is pure energy, and usually the gamma symbol is used, and a couple of zeros are put on there. Sometimes as well, there are other sort of particles that we come across in nuclear chemistry. There are positrons, which is like an electron with a positive attitude. So they also use the same symbol, the beta sort of symbol, but it is +1. Or they will use the electron with a +1 as well. How do you know sort of the difference between these? Usually there's some type of indication. So if you see just the beta symbol, you probably could safely assume it is the beta particle. If you see just the beta symbol, they typically will put something like a plus or something on it to indicate that, it is more the positron that's happening. So even though they kind of use similar sort of symbols, even if they really strip it down to basic symbols, they usually will put the plus there to indicate that it is a positron. We also can see some nuclei go under an electron capture, which is basically capturing an electron. Now, up on top is our mass number and atomic number on the bottom. The atomic number, as you hopefully know, is the number of protons there are in the nucleus. That can be found on the periodic table, right? So that is the number that goes above the symbol, is the atomic number. The mass number is the number of protons and the number of neutrons there are in an atom. When you calculate the mass number, atomic number, the number of protons, number of electrons, or neutrons, they all should be positive whole numbers. So they all should be positive whole numbers. As you also know, hopefully the mass number is not found on the periodic table. So the mass number is not on the periodic table. So this number on the bottom is not the mass number. That is the atomic mass. Yeah. So way to remember that is it always needs to be a whole number. If you look at the periodic table, pretty much none of those are whole numbers. They're all decimal numbers there on the bottom. So they are the atomic mass, which oftentimes is very similar to the mass number, but it is not the same thing. So here again are some common symbols that we see in nuclear chemistry, some of which we just talked about. The proton also is used a lot in two different symbols for the proton, a P with a 1 and a 1, or a hydrogen with a 1 and a 1. And a neutron is used a lot in terms of symbols as well. So that is an N with a mass number of 1 and an atomic number of 0. And there's our electrons, our positrons, which again use similar symbols, but +1 versus -1. And obviously our couple of symbols there for our alpha particles. Now, in terms of radioactivity, they can penetrate alpha, beta, gamma, different are distances within, say, lead or even in your tissue. Alpha particles don't penetrate as far. Beta particles go a little bit further, and gamma rays go very, very far. So if you ever find yourself using radioactivity, which can happen if you work in a laboratory, you should always know what type of emitter it is as to what type of protection that you might need. It could just be a lab coat and gloves, or it could be you need some lead and a bunch of stuff and to kind of keep you safe. A lot of times, if you do work with radioactivity in the lab, they oftentimes will give you like a ring to wear and a little badge, and they develop it after so much to see hopefully you're not glowing or anything like that from the exposure. And so it's always a good idea to know what type of emitter it is, so you make sure you have yourself the proper protection. Here again, just some different symbols like we just talked about there, in case you hated the first three slides of that. Let's talk about balancing nuclear equations. And balancing nuclear equations are super hard. And it does take a little getting used to. I'm just kidding, by the way. If you know how to add and you have a periodic table, it's super simple as well. So Obviously, one thing that's very different with nuclear reactions than, say, chemical reactions is in chemical reactions, we have conservation of elements, right? So if you like start with four carbons, you end with four carbons, they may be in different things. In nuclear chemistry, we don't have any conservation of elements typically. And that's because the difference in the reactions. In a chemical reaction, the only thing that you're doing is breaking electrons, right? Breaking bonds and making bonds. That's all electrons. The most important thing about an element and what makes it a specific element is the atomic number or the number of protons. The number of protons tells you what element you're dealing with. Every element on the periodic table has a different atomic number and a different number of protons. So the main difference that happens in a nuclear reaction is the reaction is all about the nucleus. We change protons to neutrons, neutrons to protons, and all that happens in the nucleus. And what happens as a result of that is when we have a nuclear reaction, we do not end up with the same elements on the other side because we're changing protons and obviously we're changing elements. So we do not balance equations like we do with coefficients. We basically balance them two ways. We need to make sure that when we look at an equation, all of the mass numbers, which are our top numbers on the left-hand side, equals all the mass numbers on the right-hand side. So we take a look here, we got 235 and 1. That is a 236 total for mass numbers. We got a 138, we have a 96, and we do have a coefficient here, and we do times this guy by the 2. So we have a 2 there with our 96 and our 138, and that gives us 236 on the right-hand side. So this equation would be balanced because the mass numbers on the left-hand side equals the mass numbers on the right-hand side. And maybe to no surprise, you actually just do the same thing with the atomic numbers. So all of the atomic numbers on the left-hand side need to equal the same number of the atomic numbers on the right-hand side. So here that's 92 and 0, which is 92. That's 55 and 37 and 0, right? When you add up all the bottom numbers there, it's going to give us a 92 on both sides. So this would be balanced. So for example, if we have this equation and one possible way you may see it is like something like this, maybe. And maybe something's missing. So if something's missing, a good way to figure it out is to start with the atomic number because that will tell you what element's missing because that's basically the element. So again, on the left here we go, we got 92. On the right, we got 55 and 0, which means we have 55. So if we subtract those two, we are going to end up with 37. You would then go to the periodic table and find number 37. It should hopefully say RB, and that's 37. Then on the top, you do the same thing. You'll go, okay, I got 138, and this is 2. So that's a 140 up on top. And obviously, as we did before, we have a 236. You just subtract those two, and you'll end up with your 96 that's missing here. So not too bad. Your favorite friend is the periodic table, maybe, and adding and subtracting. Now, what is missing could obviously be a element or an isotope. It could also be a particle as well. So if you do something that's like doesn't really, look exactly like an element or something like that, it has a 0 for the atomic number. Maybe it's a neutron missing or something like that. But in most cases, it will probably be an element. Now, a couple of terminology that's used when you're dealing with sort of balancing nuclear equations is it goes through beta decay. What that means is it will give off a beta particle. So if it goes through like a beta decay, that means on the product side, you should have a beta particle. If it emits or does some type of emission of a alpha particle or some type of thing like that, something to do with emitting means you should put that particle on the product side. If you do some type of bombarding, so you bombard it with a neutron, that is going to be on your reactant side. So if you do some type of bombarding or shooting something at it, basically. The other thing is we saw there on the last slide, electron capture. Electron capture means the electrons on the reactant side. So those are some words that you sometimes will see in problems. Most of the things will end up on the product side. Just really something if you bombarded something or you have an electron capture, that thing's going to end up on the reactant side. Then you kind of fill it in and again, look at what is missing to get you there. So for example, if we look at this and we have PO212, it decays through alpha emissions. Write the balanced nuclear equation for this. So a couple of things we know is, first off, we would want to go to the periodic table and find our PO there, which is number 84, right? So, and because of that, that will tell us our missing atomic number, right? So that's our missing atomic number. Now, this goes through alpha emission, which basically means it gives off an alpha particle. So again, that's going to be on the product side. We know for sure we have an alpha particle. And again, you can use the alpha symbol here. You could also use the helium symbol if you wanted to. That's perfectly fine, whichever one you want. At this point, we're now looking for kind of what's missing. So at this point, we would go through. And again, I would probably start with your atomic numbers. So on the left-hand side, we have 84. On the right-hand side, we have 2. If we subtract that, that is 82. I would then go to the periodic table and find number 82. And number 82 tells me it is lead. And that is going to tell us that is the missing one that's there, and it should have an 82. Now we need to figure out our mass number. So up on top for our mass number, we have 212. On the right-hand side, we have only 4. So if I subtract that there, what is that? 208, I think, if I did that right. We end up with a 208 in this case. And now we would have a balanced nuclear equation. Not too bad, adding, subtracting. Left-hand side on top, 212. Right-hand side, 208 and 4 is again 212. 84 on the bottom, and 82 and 82. And 2 is 84 on the right. Any questions on that there? Again, not too bad. All right. So as I mentioned before, the difference between really a chemical process and a nuclear process is, as I mentioned, chemical is all about just breaking electrons. We never touch the nucleus, which is really why we conserve elements there and we have the same elements we started with and ended with. Here, as I mentioned before, it's really all about just playing with stuff in the nucleus, and that is why we do see changes in protons, which thus changes the elements that we end up with. So what's happening as we go through some of these decays, just to kind of look at it here, in a beta decay, we decrease the number of neutrons by 1 and increase the number of protons by 1. This is a neutrino, which you don't have to worry about. It has no mass or anything like that. We're not going to get too much into it. But what's essentially happening here is we're changing a neutron into a proton, and that is for the difference that we see. So if we kind of look at it stage by stage, which is not perfectly correct, what is happening in this particular case is we're going to lose a neutron, right? So we lose a neutron, which takes us down to 13 and 6, right? And we're still carbon. But then we gain a proton, which then takes us to 14 and 7 now is nitrogen, right? So overall, it doesn't look like the mass number has changed, but it really has. We kind of swapped out a neutron for a proton, but overall difference, it actually ends up being the same number when it's all said and done. But there is that change, and obviously we increase by 1, and that's what we see here. We go from 6 to 7, obviously, and 19 to 20. Mass number stays the same, even though we're kind of really swapping a proton for a neutron, and it works out the same. When we're doing a positron decay, we're really taking a proton and turning it into a neutron, and that's what gives off the positron particle that comes off. And same idea here, if you just kind of go through it sort of step by step, you kind of see what's happening. We're going to take out a proton, which will take us to 10 and 5, and that 5 is going to take us to boron. And then we're going to put back in a neutron that was formed. So we're going to add our neutron back in, And we're going to end up with an 11 and a 5 in boron. And again, it appears that the mass number doesn't change, but again, here we're swapping a proton for a neutron. And we do actually go down by 1 in this case in terms of the atomic number because of that. Electron capture, in this case, we're actually just turning a proton and electron into a neutron. So once again, we're going to sort of appear like the mass number is not going to change because we're swapping basically a proton for a neutron, but that is sort of what's happening in this particular case. And again, here we do need to go one more, or we do subtract, we end up at 17. For our biggest sort of change is the alpha, as it changes by 4 and 2. And that makes the biggest sort of change in both the mass number and the atomic number. Now, fission is the process where something that is radioactive and unstable will basically break apart into 2 new nucleuses usually. And usually will give off a lot of neutrons and energy, as we'll talk about. And as we'll talk about, spontaneous fission is just that. It doesn't need any help to go through the fission process and start to sort of break apart. We'll also talk about the idea that you can kind of force that to happen by shooting a particle like a neutron at something, and it becomes unstable and then goes through the sort of fission process of splitting off into 2 new nucleuses. Here's a table that kind of goes through that there as well. All right, so why don't you try this one here? Write the nuclear equation for the positron emission of potassium 40. By the way, potassium 40, that is the mass number when it's written like that. Potassium is 19 on the period. Okay, so let's take a look. So obviously here we have potassium 40, our mass number. We get our atomic number there from the periodic table. This is going to go through a positron emission. So emission means our positron particle is going to be on the product side. And again, you can use the beta symbol. You could also use the E symbol if you like. So now we want to kind of figure out what is missing. So we got 19 on the bottom there. We got 1 on the bottom on the right-hand side. That's an 18. So we go to periodic table there. Number 18 is argon. Now we need our top. That's 40 and 0. So that's a 40 right there. Any questions on that one there? Let's see here. They should agree, I hope. All right, so why don't you balance up these and see what you come up with here. We can go uranium 238. Obviously, we go to our periodic table there and find 92 as our atomic number. Alpha emission means we will have our alpha particle there on our product side. You could also use the helium symbol if you like. Our missing atomic number, that's 92 and 2, so that's a 90. So once again, we go back to periodic table, find number 90. That looks like, where did it go there? I was going to say that was mercury, but it's not. It's TH. So TH should be number 90. And up on top, we have 238 and 4. So we subtract that. That's a 234, I think, in that case. Yeah. Questions on that? Beta emission, once again, neon we're going to start with. 24 is the mass number. Number 10 there is our atomic number. Beta emission means we are going to give off the beta particle there. That means we have 10 and minus 1, so we actually do need to go and subtract that. That's going to give us 11, because 11 and minus 1 is 10. Number 11 on the periodic table there is our friend sodium, and up on top, 24 minus 0 is 24. Okay, not too bad. Nitrogen 13 up on top, 7 from the periodic table there. Positron emission means 0 plus 1, and again, you can use the E or the beta symbol if you like. That means on the bottom we got 7 and 1, so we're going to subtract that. That's going to give us a 6. And number 6 up there looks like carbon. And 13 minus 0 up on top is 13 in this case. Any questions on those there? Bottom one, we got beryllium 7, periodic table number 4. This is an electron capture, which means that is actually going to be a reactant. So it's going to be on the reactant side there. So that means we're just going to simply add the bottom numbers there. 4 and minus 1 is going to get us 3, which should be lithium from the periodic table. And 7 and 0 is 7. Okay. Any questions on balancing those reactions there? Not too bad. Adding periodic table, good shape. Yeah. All right, we're going to lay that up there for today.